today I want to show you this circuit right here. This is basically a circuit that I designed to show the status of IC pins. Like, for example, if I want to test that one there and that one there, or even these ones here on my old oscilloscope, I want to show the pin status all at the same time to see what's going on with the IC. And it's basically like an IC tester, but it doesn't actually give me any character definition and things like that, but it does show me the status, whether the pins are high or low, or if they're being clocked. So basically what the circuit is, I'll show you the diagram in a minute, but basically all it does is that there's a clock on here, which is that, and then that goes into a counter, and the counter, this is a 16-bit counter, so it'll count from 0 to 15, and those bits are applied to these two chips right here. These are multiplexers, 74151s. And then from there it goes into a 7400 to these resistors. These resistors on this side are put together in what's called a 2R2 ladder. And what this does is it according to the data that comes into the chip, it actually, in this case, it actually starts at a high level and goes down to 0 in steps. Okay, and what that basically does is it causes the screen on the oscilloscope to scan from left to right, or in this case from right to left. And then it goes into a 7474. Now these are two components that I put extra, and I'll show you that the reason why I did that in a minute. But basically that's all the circuit does. Here's the diagram. Here is the actual circuit. You'll notice also that I added a couple of switches here, and what these the purpose of these is to actually show the amount of pins on the oscilloscope. So for example, this switch here will bypass everything here and will allow the counter to count to the full bit capacity, in other words 0 to 15, and that's it. So it acts like a bypass. But if you flip it away from bypass, then it activates this switch right here. Now in the bypass mode, this will display 16 pins on the oscilloscope, but when you switch it away from bypass, this now controls the display for an 8-pin chip and a 14-pin chip. And I'll show you that in a minute as well. And then I'll also show you the function of how this displays on the oscilloscope. So I'm going to put this down for a second, and I just want to focus on my oscilloscope here. I actually have, so give me one sec here. Okay, so this scope right here is a workhorse oscilloscope. It's a dual channel. It's actually, I've had this for a long time. It's actually a pretty good scope. In its day when it was made, it was one of the better scopes around. This is a 30 megahertz dual trace model 1474 by B&K. And I just recently finished an alignment on this, so and it still works pretty good. The only thing that I found was that the CRT itself has dimmed down a little bit, so I think it's starting to lose its emission. But it's still visible, and I can still work with it. Now, unfortunately, this is not one of those Tektronix scopes. It's not an updated scope. It's a workhorse in the field, and it's obviously it was worth its value in its day. Today it's probably still worth something, but not what they have available today. But anyways, I decided to use this scope for my circuit because I wanted to see if I could get the display that I actually designed this for, and it does work. So what I'm going to do, so right now I have, let me just focus back on this again. So right now, what I have is I have this circuit. This wire here goes to one probe, and this wire here goes to the other probe. Now the oscilloscope itself, right there. Sorry, I'm gonna try. I have to try and manipulate this camera because I can't get in the whole picture here. Maybe if I go back a little bit, you'll be able to see it all. All right. Now this scope here has a channel B position right there, which most scopes they have that. So that makes channel A here the y-axis input to the screen, and the channel B right there makes it an x-axis input. So the y-axis is coming from this line, and the x-axis is coming from this line right here. Okay, so basically I think the scope is on. It's on, yeah. So let me just turn the intensity up. I'll turn this light off, and you'll see that when I turn the intensity up, okay, right now it's displaying on the scope 16 pins. So this is showing that it's scanning a 16-pin IC. Even though I haven't connected anything yet, the display is showing 16 pins. So it's ready to check a 16-pin IC. Because if you count, it has 8 dots on the bottom and 8 on the top. So the bottom left is pin number 1, and it goes to 8, and then it goes up to 9 and over to 16. All right, now that's with this switch right here, this bypass switch. Now, if I flip this over, I'm not sure what's position this is showing right here, but if I flip this over, okay, give me a sec here, something's not connected right here. Okay, if I flip this switch, you'll see that it now has switched to 7-pin. Because if you count, it's 1, 2, 3, 4, 5, 6, 7. So this is now showing 14. So that means that this switch, this is off of bypass, and this switch is now showing 14-pin display on the oscilloscope. And if I flip this over, it is now showing an 8-pin IC. All right, but if I flip this switch back, it goes immediately to 16. I'm not sure what's going on here. Hold on a sec. I've got some kind of bad connection here. Obviously, these breadboards, they do this all the time. Maybe, is it the ground line? I believe it might be the ground line. Oh, the ground line fell off of this one. Hold on a sec. Okay. That should be good. All right. So anyways, we're going to leave it at 14 pin because these chips on this board are 14 pins. So let me put that to 14. And what I'm going to do is I'm going to connect a cable. You'll see right here, this is a cable that I made using PCB board, and I just ran some lines here, connected some terminals so I can plug it into the breadboard. And this here, this end here will plug into these two multiplexer ICs, because those are the inputs for the circuit. So let me just go ahead and connect this, and I'll be right with you. I'm going to turn the light on here for a sec. Okay, I've got the cable connected here. These are connecting to the multiplexers, pins number 1 to 4 and 12 to 15. On these multiplexers, the 740, 151, pin number 4 is A0, and it goes all the way down and then continues on the other side, 15, 14, 13, and 12. So that will be A0 to A7. So that would be 8 inputs. This is the second chip, same thing, A0 to A7 on the other side. Those connectors come to these strips right here that plug in directly in parallel with the IC. It's in behind there. Now, if you look at the scope, I've obviously powered the IC only with 5 volts and ground. But if you look at the scope, this chip here is a 7404. It's an inverter chip. It's got 6 inverters inside, so a hex inverter, 7404 standard chip. And if you look on the screen here, you can see that it's a 14-pin chip, so there are 14 pins. And obviously, I'm going to get something to point here with. So obviously, if you look at this first pin on the bottom left, that would be pin number 1. That would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, on the 7404, on the TTL chips, most of the pin 14 and 7 are always power and ground. So pin 14 here obviously is high, so that's telling me that there's 5 volts. Pin 7 here is low, so that's telling me it's ground. So anything below these values right here on the top row, these are all high states, and the ones just below that are all low states. All right. Now, for a 7404, obviously pin 1 is input, pin 3 is input, pin 5 is input, pin 9 is input, 11 is input, and 13 is input. All the other ones are outputs. So if the inputs are all high, the outputs must be all low because they're being inverted. So as you can see here, this would be high, low, input, output, high, low, input, output, high and low, high and low, high and low, high and low. And the other 2 pins are your power and your ground. So this is telling me that the chip is good, and I'm able to see the status on each pin, even though I'm not injecting any signal into the chip. The chip, as far as I'm concerned, is showing what it's supposed to show. So that's okay. Now I can remove this. Let me remove these connectors here and put them on the next chip. The next chip is also a 14-pin. Just give me 1 sec here to connect them. It's a 14-pin, and now you can see the status of this one. Now, what you see here is you see you see 2 highs. These are all lows, and these are all highs actually, because there's no bottom row here. So now this chip here is a 7493. On the 7493, pin 5 is power. So if you count here 1, 2, 3, 4, 5, this is obviously high because that's power. Okay, this is low, pin 11, because that would be ground for the chip. So power and ground. Now you have highs here because pin 13 there's no connection, pin 14 there's no connection. The rest are all high because there's nothing being controlled on this chip, and obviously there's no clock, there's no feedback, nothing. So obviously the outputs of the 7493 are all low, in low state, because this would be 12, which would be output A, 11 would be output D, 9 would be B, and 8 would be C. So because there's no clock signal coming in here, these are all low, all right? Because this is a counter, so the chip is obviously not counting anymore. So again, this is showing me that this chip is functioning as it should, because it's you know, there's nothing weird about the outputs of this chip or the inputs or anything else. Now, you could use this to test the chips as they are working in a circuit, or like this, just put it in the breadboard here and connect the probes and see if you're getting the output that you're supposed to be getting. So this is pretty good. It's a fast tester, and what I like about it is I'm able to see the status of all the pins of the IC at one time on this old scope. Because the new scopes probably do this, but this is an old scope, so I had to, it doesn't have any of this built-in, system in these old scopes, obviously. I would also like to add a character generator to start displaying some characters on screen, as far as like high and low conditions, maybe voltages, voltage levels, frequency levels, and so on. That can be accomplished in the XY format. When you set the scope up in the XY system, where you have an independent Y input and X input, you can actually generate any type of vector system on this scope, including characters or images or anything. As long as the frequency is fast enough, you can do it. In my case, I haven't done that yet. I've been working on this circuit right here just to display these pins. So anyways, that's the system here. And, I hope you guys like this one here. This I think is pretty good. Otherwise, under normal circumstances, you could just use a probe and just probe the pins of the ICs one at a time. Kind of hard to keep track. I actually like this system better because the connector connects across the entire IC all at once, and the IC pinout status is being displayed on the oscilloscope all at the same time, which I think is great. So anyways, let me just turn the light on again. Yeah, let me turn the light on again, and I'm going to show you guys the diagram. Now, here is the diagram, all right? Not sure if you can see that. Might be kind of dark. But anyways, here is the block diagram. Basically what the circuit is you have the test clip, which is this here, and the data selectors, two data selectors, which are your 74151s. That's these two chips right here. Then you have your clock and your counter, and the digital analog converter, which is the R2 ladder, which is right here using the resistors. Now, the rest of the circuit, I actually added that because I wanted to modify this to display 8-pin, 14-pin, and 16-pin, as you saw. Here's the actual diagram itself. So for the clock, I used a 7413. This is a dual gate 4-input Schmidt trigger, all right? And Schmidt triggers are very good. You only need a capacitor resistor. The output is a nice solid square wave because the Schmidt triggers have thresholds that they must cross in order to get a sharp output. So that's the reason I'm using a Schmidt trigger. And then for a 16-bit counter, I'm using the 7493, and that will send out your binary coded decimal right here, and that goes to the output. So each time these outputs switch, you can see here that it goes directly into the multiplexers. So what happens is as this counter starts counting from 0000 to 1111, it will, 3 of those bits will go into the multiplexers, and for a specific binary data at the ABC inputs, it will select one of the 8 inputs of the chip and send those to the output line right here, pin number 5. Now, even though the signals are going in at the same time on these chips, it's only activating one chip at a time because you have pin 7 here, which is your strobe, and they're active low. So in other words, on these chips, if pin 7 is high, then the chip is disabled. Okay, you have nothing out of it. And these strobe inputs must be low in order for the chip to output any kind of data coming in to the input lines, to the output here, which goes directly into the Y, the vertical input of the oscilloscope. And the way that's accomplished is with an inverter. I'm using an AND gate here as part of this package right here, which is the fourth gate. I'm just using it as an inverter. So when pin 11 here is low, that low is basically applied to the top gate. So only this top chip, this top chip here is scanning the pin status of the IC that you have under test. This low is converted by the NAND gate to switch this one off, because this low will be changed to a high, which disables this one here, and this one is enabled. So so when pin 11 is low, this chip is enabled, so only the output from this chip is being sent out to the Y, vertical input of the scope. When the count reaches 7, in other words, 111, pin 11 is still 0. The next count pin 11 will change to 1, to a 1, and this will start at 0 again. When that changes to a 1, this gate will now switch this chip on and disable this one here. So now it scans the bottom part of the chip. So you can see that it scans alternately. And each time it scans alternately at the speed of the clock, it will output whatever status coming into the pins of these multiplexers to the output here and to the vertical input. All right, now the way you scan it across the scope is you must produce a step to move the horizontal, the x-axis of the oscilloscope a short distance to the right, to the right, to the right, to the right for every single scan that it does. And that's the purpose of the R2 ladder, because the R2 ladder creates a step. Okay, in this case, it starts high and it goes low. So the step is actually going like this downwards to 0. And then when it resets, it'll go back up high and it scans again. But this scan going to the x-axis is actually moving the beam of the oscilloscope from from right to left, or left to right. No, I think, yes, from right to left. And that's basically the whole system. So as this R2 ladder is scanning the horizontal beam, this system here is producing an output at the vertical input of the scope at different points. All right. So now the purpose of this resistor right here is that you must. What this does is it puts a voltage. The voltage coming from pin 11 is applied to the vertical input to increase the height of the primary scan and then the secondary scan, so that you get a separation on the scope between the bottom, between the top here, top dots, and the bottom dots. You get that separation. That's caused by this resistor. I found that 820 ohms basically fills the screen right there pretty good, so I left it as 820. Now, also what I've added here, originally pin 11 just went up to the AND gate here and up to the pin 7 of this IC. But what I've done is I've modified this a little bit. What I've done is I've added, as you can see, another NAND gate here. This is wired as a 3-input AND gate. So there's the actual final gate, but you can actually wire in a 7400 as a 3-input AND gate. And the reason I chose a 7400 is because I can utilize all 4 gates in the chip. You know, I could have used this 3-input AND gate, like a 7411, I believe, but that would leave me an extra gate in the chip, and I really hate leaving unused gates in an IC. I would rather use all available gates in an IC. So 7400 suits that purpose very well because 7400 contains 4 NAND gates, and I'm utilizing all gates to produce a 3-input AND gate, so that's the reason I have a 7400. And then you'll notice that I've added these switches, which are these switches down here. Oh, you're not able to see that. Okay, hold on a second. These switches right here. One is a bypass, and the other one will control the bypass, which displays 16-pin, and this one here, which will display 8-pin and 14-pin. So I've added it out of pin 11 before it's applied to the multiplexers. And then from there, I've also added a 7474. This is a flip-flop. So the data at the D input is sent to the Q output on the rising edge of the clock. And the way I've accomplished that is by taking the signal from pin 11. Every time pin 11 goes high, it comes through the switching system and it comes into this capacitor. This capacitor is basically grounded on both sides. The 820 will ground the negative side, so the clock is at low on this side. On this side here, this is also at low because the signal from pin 11 originally would have been low, but every time it switches high, there's a momentary high pulse that comes across the capacitor as it starts to charge through the resistor. So that high rising edge of the clock will activate this chip. It'll send a clock pulse into the 7474, which is what's needed because that's what triggers this IC. And then the output from the Q output, which is complementary to the not Q, which is complementary to the Q output, will be, which is directly connected to the data input, which will be opposite to what the Q is. Obviously, the Q output will change to whatever the data input is on that rising clock edge, and that Q output is now applied back to the switch to go into pin 11 right here. So the reason I did that is because I want to be able to change the status of pin 11 earlier than the full count of the this binary counter. So in other words, in order to display 8 pins, you must change the status on these ICs at when the chip counts to 4, okay? So when it counts to 4, it's actually pin number 8 will output a high pulse because it actually starts at 0, 0, 0. That's the first digits that this will output data, and then it'll go 0, 0, 1, 0, 1, 0, so that would be 3, and then the fourth one will be 0, 0, 1, and that 1 is on the 8th pin. So when you select the switch to display 8, as soon as pin number 8 changes status, that 8 pulse comes through the switch here, you can see, and it goes directly into the capacitor. It pulses this, the output changes states, and it comes through the switch here up to pin 7 of this gate, and then on the 8th pulse, this pin here will change status and switch the inputs to these 2 chips to display 4 pins on the first 4 pulses for this chip, and then the second 4 pulses from this chip. So basically, it will only scan from D0 to D3, which would be 1, 2, 3, 4, and D0 to D3. And between the 4 pins on this and the 4 pins on this, it'll display a total of 8 pins on the scope. In the case of displaying 14 pin IC on the scope, you need to reset this on the 7th pulse, because on the 7th pulse, obviously, you're going to have a high, high, and high on pin 9, 8, and 12, and that's why you need a 3-input AND gate, because you must take the signal from all 3 pins and combine them together as one output, and that one output is fed to the bottom part of the switch as a pulse to switch the conditions of the strobes at the 14-pin level. In other words, 7 on the top and 7 on the bottom, so that's 14. And that's why I've added these components, and that gives me the option to switch the positions of the pin status display on the oscilloscope from 8-pin, 14-pin, and 16-pin. So anyways, it's, I can go on with the explanation. It gets kind of complicated, but anyways, the design here is actually not that complicated. It's very simple. And the R2 ladder, the reason that I wired it like this to start at a high level and go down to low is because I wanted the display on the oscilloscope to show all high conditions when it's idling. All right, so anytime a pin goes low, it'll drop down from the top level. So that tells me that I know that the bottom level is low, and anything on the top levels between these pins is a high state. And I've also wired it so that the on the left side, bottom left, would be pin number 1, and it goes across this way all the way to the last pin, and then goes up and over to the final pin on the top left. So that would simulate the actual IC. If you're looking at it from the top, the dot on most ICs in this position would be on the bottom left, and that designates pin number 1. So I tried to display this as you would be seeing the IC directly. So anyways, guys, I think I'm finished with the explanation here. I don't know what else to tell you, but this is the diagram. This is the circuit. You could see that it displays very well. Let me take the light off so you can see better. So I'm just going to take this off and put it back on the 7404. I got to be careful with these right now because they're kind of, I just put them together real quick. They are kind of flimsy. I have to really secure these things, build it much better. So that's that part of the chip. This is that part of the chip. Now, if you look at my scope, you'll see how the status changed. I am now checking the 7404 again. And I'm still in the 14-pin mode here, according to the switch. So because the chip is 14 pins, I'm displaying 14 pins. And a 7404 is exactly what you see here, because you have 6 gates inside this chip. These 2 pins are 1 gate, the 2nd gate, 3rd gate, 4th gate, 5th gate, and 6th gate. These 2 remaining pins are ground and B+. Okay, so you have to know a little bit about the ICs that you're looking at, obviously, but even if you don't know, this system here will show the status of what an IC is supposed to be doing. You can also check any stock that you have with this to see if any of the ICs have some bad sections in them, some bad gates. And they're not supposed to be doing what they're doing. And also, for example, a 7400, I don't have one available right now, but a 7400 would show, for a floating input, it would show a high and a low, because that would be 1 gate, and then high, high, and low, that would be the 2nd gate. Pin 7 would be ground again. These 2 would be both high and low, and these 2 would be both high, and that would go low. And this would stay high because that would be V+. So if you get a display like that for a 7400, then you know the 7400 chip is good. So even if you don't use this particular circuit to check in live systems while it's being powered, You can certainly check your integrated circuit in your stock to find any bad ones, and maybe you can weed them out that way, or just do it manually, individually. I found that this system is much faster, although everything right now looks messy. Once it's all put together with connectors, a box inside of a box, and everything else, it'll look great. All you're going to see is the external ribbon cable and a couple of jacks that will plug into your scope on the y-axis, x-axis, and that's it. So guys, with that, I hope that you've enjoyed this video. Don't forget to subscribe if you haven't done so as of yet, and I will continue to give you some other little circuits like this that maybe you guys might be interested in, and also with diagrams so you can build it yourself or modify it yourself to your content. So thank you very much for watching. Until next time, have a great day, and yeah, we'll catch you later. Thank you.